So let me now talk about a very important idea called failure detectors. So this was an invention that was done in the 1990s. So the 1990s was actually a very important time for distributed systems. Let me give you some little bit of history. So if you look at the timeline here, so here's the year 2000, 1990, 2010, and now we're almost 2020, we're like here somewhere, or here, 2019. So distributed systems, so the internet, TCP, packet switching, was here. The internet started here in 1970, which was called ARPANET. And people did not really understand distributed systems in those days. So here was the glorious area of Leslie Lamport, starting in the 80s, where he started creating this area of distributed algorithms, and many people started working on this. So in the 1990s, there's some point where failure detectors were invented by a guy named Sam Tueg. And before failure detectors, it was a very messy field, distributed systems. After, it was much cleaner. Okay? It was very messy because every single algorithm had to do all of the messy synchronous, asynchronous inside the algorithm. Failure detectors made the algorithms very clean because they encapsulated this very nice box called the failure detectors. And here, it gets even cleaner. So here is the Guerra and Rodriguez book, which is actually a very important, this was, I think, it was a little bit later. I think it was 2007, came out first. This book is the first one, so the course is following this, where you really have this layered structure. So this kind of structure. Before this, everything was kind of a mess. All the algorithms were kind of messy. And after this, so it started out becoming very clean with the notion of failure detectors, which are single boxes that encapsulate the timing. And then it became even cleaner when we have this layered structure in this book, where this book is actually, there's many books, other books here, but if you look at the earlier books, they're kind of a mess. I mean, they're not very well organized. This is where it starts becoming organized. So the whole area of distributed algorithms is very, very young area. So it only really starts becoming a clean discipline around the middle of the year 2000. Before this, it was very young area. It starts getting a little bit mature here. So not so long ago, actually. Yeah? So what I want to talk about now is failure detectors. So we want to go away from the messy period and want to show things in a very clean way. So many things we'll see in this course, they seem very simple, but some of them took a long time to understand. And the people that were very simple. So failure detector is like an abstraction. It's a box. It's a black box, which tells you information, sends out information about failures. And the idea is that all of the knowledge about synchrony, partial synchronous, asynchronous, and so on, the timing assumptions about synchrony are inside this box. Heartbeats, timeouts. So failure detectors are going to make that very clean. So the rest of the algorithm does not have to work about it. So the failure detector is going to give messages. It's going to say, for example, node PI has crashed. Or it's going to say, for example, I suspect that PI has crashed. Maybe it crashes. Or maybe it's okay. PI is not crashed. Resume, it's okay now. So I think maybe PI crashes, but now PI I think is back to normal. So this are the messages that this failure detector is going to give us. So it's going to tell us suspicions. So this box is kind of there's some kind of a demon inside here that looks at the network and tells us whether things are going okay. Okay, so the black box gives these suspicions. How accurate is it? How smart is the failure detector? Well, it depends on the model. Are we in a synchronous model, partially synchronous, or asynchronous? But this notion was invented around 1990, a little bit after maybe. This was a major step, very important step to make distributed algorithms look very nice in a mature field. So the concept of failure detector is very important. Okay, so let me make let me erase here. Say some stuff about failure detectors. So in this course, the failure detector is like a black box. It's going to talk to the network. So here we have the channels. And it's going to give information to the algorithms we want to do. Okay, so this failure detector is like a box. It's going to do things here, and it will tell us what it thinks about the failures. So typically what it will do is it will exchange heartbeat messages. So if we have two channels, the failure detector is on two nodes here. We'll exchange heartbeat messages. So the failure detector will send periodically a message, and it will measure the round trip time. If the message does not come back, if it takes longer than the round trip time, the failure detector is going to suspect, maybe the node has failed. So usually it's 10 milliseconds, okay, round trip. But I wait 10 milliseconds and nothing comes. Then I suspect that the node has failed. But maybe the message comes after all, after 100 milliseconds. And the matrix says, okay, I don't suspect you anymore, but I have to update the round trip time. So if I receive a message from a suspected node, I will revise the suspicion and increase the timeout. So the failure detector is like using an algorithm to figure out what the bounds are. Okay? It's doing heartbeat. If there's a timeout, it will increase the time. And if there is a bound, eventually the timeout will be, there'll be no more timeouts. Okay? But if the system is truly asynchronous, the failure detector will never stabilize. So once the system becomes synchronous, the failure detector will no longer make mistakes. So you see how it works? So basically the failure detector in this period, when I have a time here, the beginning when the system is asynchronous, and then eventually the system becomes synchronous. So starting from the beginning, the failure detector, it's going to make mistakes. The failure detector makes mistakes. But after the system becomes synchronous, eventually, a little bit later, the failure detector will figure it out, and it will have no more mistakes. And it will be correct. Okay? So typically, that's how it happens. So the algorithms have to tolerate mistakes from the failure detector, but they can be sure that eventually, there's going to be no more mistakes. So this is kind of an important property of the failure detector. It starts by making mistakes, and eventually it will make no more mistakes. Okay? So that's kind of the intuition. Let's be more precise now. So I want to be precise now about failure detectors. So you see the intuition, eh? So the algorithm gets information. Sometimes it's wrong, and sometimes it's right. And the algorithm has to use that. Okay? Let's now be more precise about failure detectors. There's actually two kinds of properties of a failure detector. One is called completeness, and the other one is called accuracy. Okay? Completeness means if a node crashes, the failure detector should detect it eventually. Okay? So when a node crashes, the failure detector, it should tell me that. It should not forget. It should actually tell me about any node that crashes. So it has to be complete. And the second requirement is accuracy. Okay? The failure detector can make mistakes. It can take a node that's alive and it'll tell me the node crashed. It's a mistake. Okay? So accuracy means there's no mistakes on the it will never tell me that a live node has crashed. So you see there are two opposite properties, eh? So the completeness, it will tell me eventually that the crashed nodes have crashed, and accuracy means that it will not make mistakes about a live node. It will not tell me that a live node has crashed. But sometimes we don't have all of these properties, okay? So we want this, completeness and accuracy. So we want the failure detector to be complete and accurate. So basically we want the failure detector to be perfect, okay? Okay, of course we can always do each of them separately, but it's hard to do both. So how can you trivially achieve one of them? Well, just tell me all nodes crash always. Well, of course I will notice all the crash nodes. Just tell me all nodes are alive. Then I will never make a mistake with an actually alive node. But the trick is both. Huh? So it's very similar to safety and liveness. The trick is you want both of these properties. Huh? Okay? So we can actually add failure detectors to our formal model. So that's a possibility. So we have the state of the node. We also have the failure detector state of the node. Okay? And then the failure detector state is updated by some magic function called the failure detector function. So it can be part of the model. Huh? So let's talk a little bit about the properties that this function has to hold. So there's a property called strong completeness. So this is kind of the best one. Every crashed node is eventually detected by all correct nodes. Okay? There exists a time after which all crashed nodes are detected by all correct nodes. So eventually means always after finite time. Huh? So this is a property that we're going to assume very often. Okay? So is this a realistic property? What do you think? Can you actually build a failure detector that is like that? Huh? Well, in a sense, yes. Huh? This is a kind of realistic property. Yeah? A correct node can try to communicate with many nodes, and eventually, if the node has crashed, the correct node will notice that. All the correct nodes will notice that. Okay? But there's also actually another property called weak completeness. Because it's not always possible to do strong completeness. Maybe there's only one node that will detect whether the node's crashed. So maybe this one node is like privileged. It sees all the other nodes, but the nodes cannot see each other. Huh? A privileged node with good view of the others. So, for example, it's like, how you can get the intuition of this? So it depends. So, let's say you have a football field. You have a person standing in the middle. He can see all of the spectators. And if one spectator faints, falls down, he can see it. Okay? So this person on the field has a privileged view, sees all the nodes. But the spectators cannot see each other always. Huh? they're sitting in the bleachers, they cannot always see each other. So sometimes some systems are like this. They have like a special privileged node, and this node can see all the others, but the nodes cannot see between. But this node can see all of them. So some systems are like this. Strong completeness is when all the nodes can see each other. So it's kind of extreme case. So weak completeness of strong completeness. And then, so this is where you see the crashed nodes. You also have the accuracy. So we also have strong and weak accuracy. No correct node is ever suspected. That means if the node is correct, nobody is ever going to think that it crashed. P does not suspect Q unless Q has crashed. No mistakes. So is this realistic? In a partially synchronous system, is this realistic? No, you're going to sometimes make mistakes. So this is actually hard. So this is not so realistic, but it's like ideal. You never make mistakes. Okay? Strong assumption, requires synchrony. So no premature timeouts, but that's not really possible in a partially synchronous system. And then you have weak accuracy. There exists a correct node, which is never suspected by any node. So not all of the nodes, but there's one node that you won't make mistakes with. So one node that you have a strong connection to, okay? But you can make mistakes with other nodes. But this one special node, this one correct node will never be suspected. A privileged node that is always seen. So it's kind of this case also. So everybody in the football field can see the players. Okay, so the players, so this is like, the football field is like weak accuracy. And the players will never be falsely suspected. You see them playing. And if the player falls down and breaks his leg, you can see what happens. But the spectators can make mistakes with respect to themselves. Okay? So you see, this is kind of different possibilities for the failure detector. And then you can talk about eventual strong accuracy, eventual weak accuracy. So this can be eventual. That means in the beginning you can make mistakes. So eventual means after some finite time. That means you can make mistakes in the beginning, but after some time you make no more mistakes. Or here, in the beginning you make mistakes, after some time you make no mistakes with respect to one node. Okay? So this is much more reasonable. This is actually pretty weak because we don't know when. Okay, eventual. But this is actually closer to partial synchrony, yeah? Okay? But let me talk now about some practical failure detectors. So there's actually a couple of them, but I want to talk about only two right now. Here we have 4 detectors. So main established detectors. So one detector is called the perfect detector, and it's called P. We're going to call it P. It's strong complete and strong accuracy. So strong complete, it sees all the nodes, see all failures, and strong accuracy, never any mistakes. That's pretty nice, eh? This is a pretty good one, huh? Perfect failure detector is like the best one. It sees all the failures, all the nodes see all the failures, and they never make mistakes. If a node fails, if they think it fails, it really fails. So this is the best one, okay? It's called perfect detector. But then there's another one called the eventually perfect detector. Let me just talk about those two for now. So it's also strongly complete, but it's only eventual strong accuracy. So this one also is very important. It has a special name too, and it's basically a diamond followed before the P. So this diamond is a notation coming from temporal logic, and it means eventually. It means in some finite time in the future, is what this means. So some finite time in the future, the detector is perfect. So this detector starts out by making mistakes, but after some time, it doesn't make mistakes anymore. So the two really main detectors are the P and the eventually P detectors. Okay? Then there's other ones. This one is called strong, even though it's weak, accurate. Why is it called strong? Well, because for historical reasons. It's a leftover from the messy period of distributed systems. Also, you have eventually strong. So strong and eventually strong, the difference is that it's with respect to one node always. Huh? It's always with respect to one node. Whereas this one, the strong accuracy is for all nodes. The weak accuracy is there's one privileged node. And eventually means you can start out by making mistakes, and later on it will make no more mistakes. So I want to talk about these two now. Perfect and eventually perfect. In this course, by far, these are the two detectors we're going to use. So the perfect one, of course, is the one we want always, if we can get it. So this is the ideal one, the perfect one. So we're going to build algorithms that use perfect failure detector. But we're also going to build algorithms that use an eventually perfect detector. So this one, the second one, this is what you usually get on the internet. Okay, eventually perfect. And but the algorithms can sometimes be complicated. Perfect is you get it on a synchronous system. Sometimes you can get it on other systems. You can get it on local area networks. You can get it on clusters. But on the internet, it's very hard to get this one. So usually you don't have the luxury of this perfect detector. Usually we're going to do perfect, eventually perfect. So in the course, what we're going to usually do is we're going to make an algorithm for perfect, and then we're going to try to update the algorithm so it also works for eventually perfect. Okay. So perfect and the algorithm for perfect is usually going to be pretty simple, but maybe it doesn't work if the failure detector makes mistakes. Huh? So basically what this means is that it makes mistakes in the beginning. Makes mistakes in the beginning. So mistakes in the sense that it will suspect the node to crash, but the node really has not crashed yet, or will never crash. So let me show you how to specify these. So the perfect failure detector is a box, okay, with one output. It's an output, and there's one message that can come out of this box, which is called crash PI. So this box can send messages, crash messages, notifies that PI has crashed. And there's two properties here, strong completeness and strong accuracy. Okay. So strong completeness and strong accuracy. So we can actually see whether these are safety or liveness. Huh? So strong completeness means that if a node fails, it will eventually tell you that the node has failed. Is that a liveness or safety property? You tell me again. Life is tough, huh? So if a node fails, I have a prefix of an execution, and so far the system doesn't say anything. But maybe I can extend the execution so that it sends me a crash message and it will tell me in the future. Huh? If there's life, there's hope that it will tell me, right? So what is this? I basically told you, huh? It's liveness, right? And strong accuracy is a safety property. So accuracy is about mistakes. So assume there's a live node, and it tells me that node has crashed, but it didn't really crash. That's a mistake. The poor failure detector is broken, huh? I broke it. Oh, it's terrible. So that's a safety property, huh? So completeness is like a liveness property. Accuracy is safety property, huh? Okay? Safety liveness is everywhere, huh? Eventually, every node that crashes is permanently detected by every correct node. And accuracy, if a node is detected, then it really has crashed. Okay, so safety liveness, we did it, huh? Okay, so this is the perfect failure detector. Liveness and safety. We can implement this. How do we implement P? In a synchronous system, it's pretty straightforward. So assume there's a transmission delay between two nodes, maximum delta, and every certain time, gamma time units, it sends a heartbeat message. And it waits a certain message, gamma plus delta. Okay? So gamma is the time between the timer, and delta is the transmission time. If it did not get a heartbeat, so each node is supposed to get these heartbeats. If it did not get a heartbeat from PI in this time, then it knows for sure that PI has crashed, huh? Because PI is sending these messages. So because of the synchronous system, you can be positive that the node has crashed. Okay? So P is very easy to implement in a synchronous system, huh? And you can prove it's correct. You can prove these two properties. So I will prove it now. We're not going to prove everything in the whole course, huh? But just to show you. So the strong completeness. Okay? A crashed node, it will not send the heartbeat. Eventually, every node will notice that, because that heartbeat has to arrive. So it is strongly complete. What about accuracy? What about the mistakes? Can it make mistakes? Huh? What is the maximum time between two heartbeats? So, because the messages, when I send a message, it takes maximum delta, but maybe it's faster. Okay? So I get a message here. What is the maximum time between these two? That means if this one is the fastest, and this one is the slowest. It's gamma plus delta, the timer time plus the message timer. You see, the maximum time between two messages is gamma plus delta. If the first one is as fast as possible and the second one is slow, and you add the time in the middle. Huh? So gamma plus delta. So if you wait that amount of time, you must get a message. And if the node is alive, you will get it. And if you don't get it, then you know for sure the node has crashed. So there's no mistakes. You will not, if you wait this time and you get no messages, you say the node has crashed, it will not be a mistake. Okay? So that's strong accuracy. So in a synchronous system, you could build perfect failure detectors. So that's very nice. Problem is, most systems are not synchronous. Huh? Okay, so that's the perfect failure detector. That's the one we like. There's now the eventually perfect one. This is the one we usually have. This is the one we usually are stuck with. Okay? It has two messages. So it suspects a node, and maybe it will restore if the suspicion is wrong. Okay? So if I get the message suspect P, the failure detector, it suspects. maybe P has crashed. But maybe it's a mistake. If I get a message, restore P, no, the node is okay. It's not suspected anymore. So it can make mistakes and it can correct the mistakes. Okay? So it has two properties also. Strong completeness, but eventual strong accuracy. That means eventually no more mistakes. Okay? It can start out by making mistakes, but since it's an eventually perfect failure detector, after some time it will make no more mistakes. Okay? This, you can actually implement this in a partially synchronous system. So in a partially synchronous system, we have this failure detector. Okay? So eventually some bounds exist. So the node will send a heartbeat every gamma time units, and it waits a certain time. If it did not get a heartbeat, then you suspect. It's like timeout. You suspected. But if the heartbeat comes later, and you've suspected it, then you do a restore, you remove it from the suspected list, and you increase the timeout. So basically the timeout is going to keep growing. It's going to keep growing as long as you get heartbeats. So if there's some bound, eventually the timeout is going to be bigger than the bound. Okay? So the heartbeats round trip, eventually it's going to be bigger. So if the bound exists, the timeout will get bigger and you will have no more mistakes. If the bound does not exist yet, well, then it keeps making mistakes. But eventually some bound exists, and after that point, the timeout will eventually be bigger than the bound, and there will be no more mistakes. You see how it works? So eventually perfect failure detector, the two properties, so you can prove them. So strong completeness as before, which means that if a node crashes, no messages, you will suspect it. And what about the mistakes? So if when you make a mistake, I suspect P and it's inaccurate. I increase the timeout. So each time I have a suspicion that's wrong, I will get the heartbeat and I will increase the timeout. Eventually, two things happen. First, the system becomes synchronous, and T becomes bigger than the unknown bound. So I need these two conditions. But I know that I will eventually have both conditions. Because eventually it becomes synchronous, it's partially synchronous, and since T will always be growing, it'll eventually be bigger than the unknown bound. Okay? And after that point, there will be no more mistakes. You see? So there's like these two conditions, when the system becomes synchronous and when the bound is bigger than the actual bound. So this is the failure detector you get in a partially synchronous system. Partial synchrony. You get eventually P, and synchrony. In a synchronous system, you get P. So this one, eventually P, is the one we get for internet. We will have this one, okay? This is the failure detector that we get most of the time. Okay? So let me stop here for today. So when we build our algorithms, we're going to assume these black boxes. Okay? When we build a consensus or broadcast, we're going to assume either a P or an eventually P. Okay? And in internet, this is the one you get. So you see how to implement it. You can implement the eventually P. So this is the one you have to live with. Okay? So we're going to be, this one will be our friend after a while. We'll be very good buddies with this guy. This guy is like perfect guy. I mean, it's nice to have the perfect one, but you never have it in real life, okay? In real life we have this one, and it's not too bad actually. It's actually pretty nice. We can do a lot of stuff with this guy. So at the end of the course, you're going to feel very comfortable with this guy, with the internet guy. Eventually P. Eventually P is the foundation of all the distributed algorithms. we're going to see him. This is the one. Okay, so I stop here. So you guys are going to be very familiar eventually.